Okay, so in order to do this, I'm going to use that the total kinetic energy before is equal to just the kinetic energy of object A before, or initial, plus the kinetic energy of object B initial, plus the kinetic energy of object C initial. And the way I'm going to calculate each of those kinetic energies is I use the momentum of A initial. It's a vector, but I'll take its magnitude and square it, divide by twice the mass of A, because this is the kinetic energy of object A. It's 1/2 mv squared, plus the same thing for B. Very carefully, I have to divide by a different mass because the kinetic energy of object B is associated with a different amount of matter or a different inertia. And then there is also the term for C, again, a third different mass. So in order to report what happens to the kinetic energies, I need to know masses. So, so I'm going to say, just for the ease of calculating without a calculator, because in this case, all I want to do is learn about the kinetic energy. Like, maybe I could just have the experience of messing around with it. I'm going to I'm going to make up some masses. And I'm going to choose a mass that's particularly easy to calculate with. You'll see what I'm going to choose. I'm going to choose that MA, MB, and MC are all the same mass. Yeah, and the value is 1/2 of a kilogram. So that's going to be my choice. The reason I choose 1/2 of a kilogram is because it gets doubled. So what happens in the calculations is I'll always be dividing by 1 kilogram, essentially. So let's do that. So now, let me put this out of the way. So the kinetic energy initial total is equal to, so it'll be, it's hard to keep track of the multiple pieces of paper, but you can see what I have to calculate. So I want to calculate this thing, which is these vectors, and here are those vectors, PA, PB, PC. So, so in order to do this, I guess I can't just directly write them down. I know that what I need to do is take the magnitude squared of each of those vectors. So I'll do that now. So piece of AI squared is equal to, this one's really easy. The way you do this is you go p sub ai vector dot product p sub ai. That will give you the magnitude squared. It's just the dot product of the vector against itself. So this is 3 units, right? Kilograms meters per second. So 3 units, special units, I hat, dotted with the very same vector again. So I hat dot I hat is 1. So that's I hat dot I hat, and then 3u times 3u is 9u squared, and this is equal to 9u squared. 9 kilograms squared, meters squared per second squared. P sub bi squared equals p sub bi dot p sub bi equals, so p sub bi is here, minus 2uj hat, so minus 2uj hat, vector dot product with minus 2uj hat. So minus 2u times minus 2u equals 4u squared. J hat dot j hat is the vectors dotted, and then you get 4u squared, that's a 4, u squared, j hat dot j hat is 1, just like I hat dot I hat. So this one, p sub c I magnitude squared equals, so it's p sub c I dot p sub c I, so p sub c initial is a little bit more complicated. It's actually extends out into both I and j. Some of you might be fast enough to recognize this as the hypotenuse of a 3, 4, 5 triangle. 9, 3 squared plus 4 squared, right? 9 plus 16 is 25, and the square root of 25 is 5. So this actually, we know the answer is 5 units squared. Or actually, sorry, it'll be 25 units squared as the magnitude squared. But let's see it play out. So it'll be 3 I hat plus 4 j hat, vector dot product with 3 I hat plus 4 j hat, and I am moving this special unit outside, and there's one for each of the terms, so or each of the factors, so it shows up here. So this is, maybe I'll put it first, and then it goes 3 I hat dot 3 I hat plus 3 I hat dot 4 j hat plus 4 j hat dot 3 I hat plus 4 j hat dot 4 j hat. What I did is known in algebra as the FOIL. Some of you have seen that, I'm sure, in your algebra classes and stuff. So the outcome of this is pretty quick. It's u squared times 9 I hat dot I hat, just like up here. So that's what happens there. This one, though, because I hat dot j hat is equal to 0, that term does not show up. It shows up as a 0. This term is the same. J dot I is also 0, and it's because these two vectors are perpendicular. The dot product of perpendicular vectors is always 0. You don't have to calculate anything. You just recognize them as perpendicular. So these are zeros in the middle, and then this is 16. J hat dot j hat, but j hat dot j hat is 1. Excuse me. So this is 25u squared. So what this leaves over for us is, remember, we're calculating kinetic energy total. So the kinetic energy total initial equals, so it's this squared over 2m, but 2m is 1. Remember, so here is p sub a initial squared. We're going to divide by 2m, but since m, we chose this sort of simple value just to see what would happen. We'll be dividing by 1 kilogram is the unit that we're going to be divided by. So this is going to be, so 9u squared over 1 kilogram plus 4u squared over 1 kilogram plus 25u squared over 1 kilogram. But u squared over the kilogram is equal to, do you remember u is the SI units of momentum? So it's a kilogram squared, meter squared per second squared, divided by a kilogram. So this is kilograms meters squared per second squared. This is exactly called the joule. So u squared over the kilogram is the joule. So u squared over the kilogram is the joule. So it'll be 9 plus 4 is 13, plus 25 is 38 joules. So that's the initial kinetic energy. So that's the kinetic energy that came into our problem. So there is 38 joules of kinetic energy coming in. The question is after the collisions, what's the kinetic energy afterwards? So we'll keep this in our radar screen, but let's go and calculate now the kinetic energy total final. So we just need all of the final numbers. And if you remember, P sub C final, we solved for it a little bit earlier. It's got this value, 2u I hat. So I'm going to scrub out the fact that we don't know it and put in that we do know it because we finished that part. So let's do this. And I'm going to do it a little bit faster, but if you, I think it would be worth your time if you're not comfortable squaring these vectors really quickly like I'm going to try to do and try not to get wrong. You should be more careful and do it yourself. So kinetic energy total final equals, so it's going to be P sub A final squared. This one, we got to square this one, and check it out, because it doesn't seem to have changed, that kinetic energy didn't get altered. So it's just 9u squared, and divide by 1 kilogram, plus PB final squared. So this one we do need to do, so I'll just do it right in front of you. It's going to be, so I need to square this. It's essentially just this squared plus this squared. So PB final magnitude squared equals, it's going to be 1u squared, right, plus 2u squared. So that'll be 4u squared plus 1u squared is 5u squared. Also over a kilogram plus, and then the last one is here, so 4u squared over the kilogram. Cutting to the chase with the units, same thing plays out again. So u squared over 1 kilogram is the same thing as the joule, and I've got 9 plus 5 plus 4. 9 plus 9 is 18. Whoa. Lots of missing kinetic energy. But momentum is conserved. So we watch the kinetic energy decrease. This type of mechanical energy can be converted into other types. Depending on the types of collisions, there's a lot of other details that we could try to insert to try to figure out what happened to this kinetic energy. Did it become sound, or did it become, well, actually it wouldn't have become sound because we don't have any air to carry away the sound energy, so it wasn't sound. Maybe depending on the types of particles these are, maybe light could have been emitted, or maybe the particles warmed up or something kind of interesting like that. But nonetheless, just on face value, this is the initial kinetic energy and this is the final kinetic energy. It looks like 20 joules got hidden. So 20 joules converted to other forms of energy.